Hi, my name is Josh, and today I'm going to be going over the differences between engineering stress and true stress. Now, engineering stress is known as Young's modulus times the elongation of the material. So you have Young's modulus, which is a constant defined for every material, times the ratio of which you elongate the material. So when you pull on something in the x direction, you multiply the ratio that you elongated it by times Young's modulus, and that'll give you the stress that the material's under. Now, stress is force over area, it's pressure. So a material that has a higher cross-sectional area is able to undergo a lot more force at the same stress value. So when you have a beam that's thicker, it's able to undergo a lot more force before it breaks because it'll have the same stress as a beam that is thinner that is under less force. So this assumption really breaks down a little because the cross-sectional area actually decreases as we pull on the object. So the stress that you're under is not constant for you to calculate that force. While you're applying that force, the stress is varying because the cross-sectional area is going to differ. You pull on something and the mass in the center starts to shift and it's giving way and it's elongating, so the area is thinner. And we can see this in this animation here. If I pull on the cylinder, then it's going to elongate, and the cross-sectional area, that radius, is going to get smaller. And we end up with a cylinder that's smaller than our original cylinder because of the conservation of mass. All that elongation had to come from somewhere. So we have a stress that's going to be higher because it's hitting a smaller cross-sectional area. Now the difference down here is summarized by the formula Young's modulus times the elongation times 1 plus the elongation. And that's known as true stress. Whereas our estimation before of Young's modulus times the elongation is engineering stress, which is an approximation. Now here I have two pistons attached to a rectangular prism of dimensions 1 by 1 by 2. Now this rectangular prism has a Young's modulus value of 60 gigapascals, and we'll see if I elongate it in the y direction, activate that piston. On the left side you can see a calculation of engineering stress, and on the right side you can see a calculation of true stress. Now you can see how this differs. Over here we have a value of 7.5, and over here we have a value of 8.4375. So you can see it's differing by a good bit. Of course, this cross-sectional area that we're dividing by here is a 1 by 1 square. Now if I activate it in the z direction, where it's dividing by a 1 by 2 square, we'll see a stress that's a lot higher to get the same kind of elongations. So we're seeing a true z-stress that is 18.75, whereas the z-stress for engineering approximation is 15. And you can see the differences plotted below here. So we can see that this approximation is good for lower values, but when we get up into that 25% range where we're trying to elongate it a good bit, that engineering approximation really breaks down, and the true stress is a much better indicator.